All right, you're in. What was that, Jennifer? You should be. Oh, your computer died. All right. All right, yesterday we discussed plate tectonics and the continental drift theory. Let me make this a little bit bigger for everybody. All right, really quickly, let's look at one of these concept questions. This is somewhat what a question would look like on STAR regarding plate tectonics theory. So it says the scientists recently discovered that small rocks collected from the Franklin Mountains in West Texas and rocks collected from mountains in eastern Antarctica were actually the same age. Further research shows that the rocks were chemically and geologically the same and came from the same magma source. This discovery provides evidence of what? You can unmute yourself and answer this question. Or you may put it in the chat. All right, we got Miss Caitlin's answer. Itzel, Carla, and Valerie. All right, Miss Lizzie. All right, ladies in person, what are y'all thinking? I got the virtual ladies' answers. All right, so Nivea said you're looking at 2 answer choices. Okay, Jennifer, how many answer choices are you looking at? At 1. All right, so what are 2 of these questions that we know, or answers off top that we know we can eliminate? All right, so let me get my pen to draw. So you said I can take out ocean currents. What's another one? Okay. Why am I taking out coastal erosion? All right, so how the pieces fit together, because the continents and themselves are like puzzle pieces. All right. So now we're left between plate tectonics and glacier melting. What y'all thinking in person, ladies? Uh-oh. Okay, so magma source. That means like, in the core of the earth, it is really hot. Like when we have volcanoes, all that magma and that lava comes up, and then once it cools and solidifies, it becomes rock, an igneous rock. I believe y'all learned rock cycles in 6th grade. All right, so sometimes our science information, you might see it 5th, 6th grade, you might not see it again until 8th grade. But it's just meaning that it is an igneous rock. It's coming from the same type of rock source. Go back to our bell ringer. What was one of the evidences of continental drift? All right. The evidence was for what purpose? Plate tectonics. So what do you think the answer choice is going to be here? G. All right. Let's look in the chat. Everybody said G/B. If you put that down, you are correct. All right. So when it is time to take STAR, just carefully look at the question, just like those annotating skills we've been talking about in class. And when you take your common assessment, highlight or underline your key terms and make sure you are eliminating your answer choices. Joanna, you don't have to restart your computer where it says recording. That's what I'm doing. All right, so our learning objective today is that students will be able to describe the movement of plate tectonics to the formation of crustal features such as ridges and rifts. So by the end of today's lesson, you should be able to describe how plate tectonics causes ridges and rifts. All right, they have on here a quick review for us to do. I'm sorry, my phone was going on. All right, what is convection? Really quickly.
When heat rises, cold air sinks.
All right. When all right, Kayla online and Leslie in person both said the same thing. It's when the hot water rises and cold air sinks. All right, good deal. All right, so we're going to watch. Where did it go? Okay, we're going to watch this video to kind of introduce to us what we're going to be discussing today.
World War II. German U-boats were on the prowl. To track them, the Allied forces developed new sonar methods, and scientists were enlisted to help survey the ocean floor. When the United States entered the war, Harry Hess was a geology professor at Princeton University. But he also happened to be a Navy reservist, so it wasn't long before he found himself in command of an attack transport ship in the Pacific. To help maneuver when coming in for a beach landing, Hess's ship was equipped with a depth sounder. Now, still being a geologist at heart, he used the sounder to measure the depth of the ocean floor whenever his ship was out to sea. Now, what he discovered startled him. Until the Second World War, most scientists imagined the bottom of the ocean looked like this: flat, lined with nothing but sediment. But about 2 miles beneath the waves of the Pacific Ocean, Harry Hess discovered something else entirely. Mountains, like these here in California, with deep canyons and trenches, hundreds of high peaks that we now believe were once active volcanoes, and all of this at the bottom of the Pacific Ocean. Surprisingly, though, the discovery of the Pacific Mountain Range is not what makes Harry Hess part of our Great 100. Now, we'll get to that in a minute. To understand where all this is headed, I'd like to skip ahead to another event that set the geology world buzzing. For years, oceanographers surveying the Atlantic Ocean had taken sonar readings that indicated there was something down there, something big. In 1953, they found out what it was: a 12,000-mile-long mountain range. They called it the Mid-Atlantic Ridge. To fill us in, I paid a visit to Neil Driscoll, a geologist at the Scripps Institution of Oceanography.
One of the big discoveries that was made was that there was this ridge of underwater volcanoes that stood high above the seafloor.
How high is a mountain in the middle of the Atlantic?
The average seafloor depths are on the order of about 4,000 to 5,000 meters. The mid-ocean ridge sits up at about 2,500 meters. So they sit about 2.5 kilometers on average higher than the surrounding seafloor that's shown here in the deep blue colors.
So that's over a mile high.
Yes.
And that's where Harry Hess comes back into the story. Analyzing core samples and sonar readings from around the mid-Atlantic ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
Harry Hess was in a position that he could bring it all together. Things were spreading apart and new Earth was being generated. But if he did this for long enough, the Earth should grow. And it doesn't.
The Earth doesn't get any bigger.
No. Harry appreciated the fact that if new Earth was being generated in one area, they have to be consumed or recycled in another area.
The process that recycles the crust of the spreading ocean floor back inside the Earth is called subduction. But as our next great discovery revealed, it's all part of a much larger process, perhaps the most powerful force on the face of the Earth.
All right, who can give me a 1-sentence review over what Bill Nye just talked about? Which is 1 sentence of what you heard. Let's see who I'm gonna call on. Stephanie, I ain't heard from you today. So tell me one fact or one thing that you heard from the video. Ooh, that is not a good sign. I don't like that sign. All right, Jennifer. Give me one fact or one thing that you learned from this video. What was the video about? About what? What about plate tectonics? What specifically was been moving? Adriana? What specifically is moving in the video? What's the land underwater called? No. No. You stand on what? What is this? And if the floor is in water at the very bottom of the sea, what would that be called? The sea floor. Okay. Not water floor, the sea floor. All right, so what is happening to this? What was happening to the sea floor? It's moving. So is it coming together or is it going apart from each other? Apart. All right, good deal. All right, so what causes those plates to move? No, not seafloor, but convection currents. So convection that happens in the mantle. Remember, that's when the hot air from the core, which is all that hot liquid iron and nickel, it getting tongue tied. All right, the convection currents moving in the mantle gets everything moving. All right, so this is where we come into our plate boundaries. So when the plates of the landforms move apart, they are called divergent boundaries. All right, it's kind of like a divide. They split. All right, when they are convergent, that means they are coming together. They're running into each other. And when they transform, that means they are sliding past each other. And we're going to talk about divergent, convergent, and transform for every day of this week. And today we are going to focus on divergent. All right, so in your interactive notebook, we are going to be on slide number 5. Remember, yesterday we saved our new interactive notebook, so go ahead and pull that out. All right, I see some people already got theirs up, ready to go. I see a few people still rolling, still trying to get theirs up. Remember to save it to your Google Drive, so it's easy for you to pull up when it's time to do notes. All right, so divergent boundaries. The definition of divergent boundaries is it occurs when two plates are moving apart from each other. So when you hear the word D-I, think of the word divide. You're splitting something in half. All right, the direction that
Miss, can you go back?
I need to go back. All right. Divergent boundaries. Its definition states that it occurs when two plates are moving apart from each other. They are separating.
Okay, thank you.
All right, no problem. All right, the direction that these plates move in is a divide. One is going to the right, one is going to the left, or one is going up and one is going down. They are separating. And how are these divergent boundaries created? They're created by two things. Well, they create two things. Number one, seafloor spreading. All right, when those two plates begin to separate from each other, that's when we have the mid-ocean ridges. That is when the new seafloor is being created from those convection currents. The older seafloor tends to move away in the opposite direction as the new seafloor is created. And then the second thing that is created from divergent boundaries is ridges and rifts. For example, the Mid-Atlantic Ridge that Bill and I talked about in the video, that is almost 2 kilometers high and about, what do you say, 14,000 kilometers wide underneath the Pacific Ocean. Then there's also the Rift Valley in Africa. Make sure you're typing out what is red. And then what is in bold. So seafloor spreading, that creates mid-ocean ridges. That is when a new seafloor is created. And then divergent boundary also creates rifts and ridges, like the Mid-Atlantic Ridge and the Rift Valley in Africa. When you have both examples or both items typed out, give me a thumbs up reaction. All right, thank you, Miss Jennifer. You can either give me a thumbs up in the camera or you can do the reactions down at the bottom. I see Lizzie just did hers. Itzel just did hers. Okay, Caitlin. All right, so that means I can move on from this slide. If somebody thinks I should not move on from this slide, go ahead and speak your piece. All right, that means we can move on. All right, so ridges. I'm going to play a video that kind of shows you what a ridge looks like underneath the sea, well, in the sea. So here is showing you where the Mid-Atlantic Ridge is. It comes from where the North American plates and the Eurasian plate separated from each other. All right, so our ridges. So that's where you have the North American plates and the Eurasian plate. They are separated with each other, and during their separation, the glaciers begin to melt, given that putting cold, clear water in the middle between each plate. All right, that is like an example and a definition of what a ridge is. All right, here is an image of the Great Rift Valley. A rift is kind of just like a ridge, but it is on land, all right, and not in water. But it's still a separation of two continental plates, or two divergent boundaries. All right, well, because this is not in Peer Deck, it says to place the flags on the locations that you see divergent plate boundaries. So since I can't place you guys can't place a flag, I want you to tell me where I should circle for a divergent plate boundary. So looking at this image, where would one be located? All right, Miss Carla said lithosphere and oceanic crust is where we can find a divergent plate. All right, so right here. All right, because we're looking at those arrows, they're going in separate directions, which causes a divergent plate. Great job, Miss Carla. All right, let's see. Elizabeth and Uvia said at the continental crust. All right here. All right, you ladies are correct. All right, so you can have a divergent plate boundary between oceanic crust, which is like the ocean, and continental crust, which is land. Oh, let me clear my screen. All right, so what we're gonna do right now for the next 15 minutes is that we are going to complete the divergent boundaries practice that's posted in our Google Classroom. All right, so if you go to our Google Classroom and go to week 2.8, you should see the divergent plate boundaries. Practice, click on that. Make sure you're signing in with your Google credentials and go ahead and complete that form. This is due by the end of the day. Do I have any questions on the assignment? No. All right, let's go ahead and get busy. We have 15 minutes till our bell. That's enough time for you to get the practice done. If you have any questions for me, ladies in person, feel free to raise your hand. And ladies online, feel free to type it in the chat or raise your hand for me to answer to ask your question. All right, let's get started. The 15 minutes on the clock. All right, Miss Juliana, I see that you raised your hand. You have a question?
No, I don't. I don't need to ask a question. I was just. Never mind.
Okay, you was just checking out the features?
Yeah.
Okay. All right, ladies, I know that right now you ladies are busy working, but I do want to remind you that for RTI today, you will not have an assignment because in all of our classes, we will be watching the inauguration for fifth period RTI. But you will have an RTI assignment tomorrow. So history and science, we just switch days. And also, if you need tutoring for extra help, tutoring is today from 4:30 to 5:30. And you can go ahead and sign in our Google Classroom under tutoring or sign up for it. And tutoring will be held on Zoom. All right. Keep working, ladies.